A vector is a quantity that has both magnitude and direction. We usually represent it by an arrow, and the length of the arrow represents the magnitude. Another word for magnitude is size. So the length of the vector represents the size, and the direction that the arrow is pointing represents the direction. Examples of quantities in physics that are vectors: position, velocity, acceleration, displacement, force, field, momentum. All of the angular quantities like angular position, there's like angular equivalents of angular position, angular velocity, angular momentum. Torque is actually like kind of like an angular version of force, kind of. In contrast, so vectors are in contrast to scalars, which are numbers only. So for a scalar quantity, you only need a number. Vectors have magnitude and direction, but they don't have a specific location. You can move them around and it's still the same vector. So I take this vector and I just slide it over there, and that's exactly the same vector. This is going to be important when we do addition of vectors because we're going to move them around. Two vectors that are the same, those are an example of four vectors that are all exactly the same. So if they have the same length and the same direction, it's the same vector. In 2D, we need two pieces of information to completely specify a vector. Two pieces of information to completely specify a vector. There are different ways to do that, and I'm going to talk about two main ones right now, which is that you could do the x and the y component, x and y components, or you can do the magnitude and direction. Those look a lot like different coordinate systems. So the x and the y components, and I'll show you what that looks like in just a second, could be thought of as rectangular coordinates. That's another word for Cartesian coordinates. And the magnitude and direction can be a representation of polar coordinates. Remember, polar coordinates are like an r and a theta. And rectangular coordinates just give you the x and the y. I'll draw that of that same vector. If we have a particular vector v, how do we find the x and the y components? And what are they? What do those components look like? So the x component is usually the horizontal component, and the y component is the vertical component. If you imagine shining light straight down from above, so there's no angle to the shadow, so just straight down, the projection of v down to the x-axis is what we mean by the horizontal component, represented by that blue line right there. In a similar way, if you imagine shining a light from the left side to the right side, then what you see is the projection. Red might be a little bit hard to see. It's a red line right there, and that is the y component of the vector, or the vertical component of the vector. Put that all together and it looks like this. And then, as I said, how do we find those components? Now it looks very much like a triangle. So if we have the total vector v, the long side of the triangle is always the magnitude, represents the magnitude. That is our Vx and that is our Vy. You can get the components by doing trig. So if you know the x and the y, and you know theta, then you know SOHCAHTOA, you know that the sine is the opposite over the hypotenuse. The cosine, SOHCAHTOA, the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. So I can find Vx by the adjacent, Vx is the adjacent side to theta, it's the one that touches, and then V is always the hypotenuse. So I could say that the cosine of theta is equal to the adjacent over the hypotenuse, and the adjacent side is the Vx, the hypotenuse is the V. I can just cross multiply, and I get that Vx is equal to V cosine theta. Similarly, I can find Vy by doing the sine, and the sine of theta is equal to the opposite over the hypotenuse, which is Vy over V. Cross multiply, and I get Vy equals V sine of theta. So if you have the magnitude and direction, that corresponds to the length, the size, magnitude and direction, that corresponds to the V, the magnitude, the length of the hypotenuse, and the direction corresponds to theta. V, in this case, V just stands for any vector. I use V because it stands for vector, but also it works for velocity. And in case you want to have something that isn't always just doing position as the initial example, it's kind of nice to think of something like velocity. So for example, if you have a vector V that is 5 meters per second at an angle of 36.9 degrees. I chose that one because it's my favorite 3, 4, 5 right triangle. You could find the x component by the magnitude, which is the 5 meters per second, times the cosine of the angle, which is our 36.9 degrees. Plug that in, and to 2 sig figs, you get 4 meters per second. And you do the same thing for V sub y with the sine, V sine theta, and you get 5 times the cosine of 36.9. You get, I'm sorry, the sine, not the cosine for that last part. You get 5 times the sine is equal to 3. Sine of 36.9 degrees equals 3 meters per second. So there's an example where you are given the magnitude and direction. The magnitude is the 5, and then the direction is the angle, and you can figure out what the x and the y components are. We should also do it the other way around. What if you start off with the x and y components, and then you want to find the magnitude? For this one, I don't know if you can see the grid that comes with it, but if you can see that grid, the grid itself has, you could just count. So if you just look at the grid, if you can see it, I can see it, I can see it well enough. If you just look at the grid, the V sub x, for the one shown right there, looks like you can count, and it looks like it is 6. If we stick with velocity, that would be 6 meters per second. And then if you just count in the vertical, on the y direction, there are 4 squares, so that we could say Vy is 4 meters per second. I bet you remember the Pythagorean theorem, and that's all you need to find the magnitude. So the Pythagorean theorem says that a squared plus b squared is c squared, where a and b are the x and y sides and the c squared is always the hypotenuse. So the Pythagorean theorem says that vx squared plus vy squared equals v squared. So if we have vx and vy and we want to find v, all we do is square them and add them. So for this example, we would just take the 6 squared plus the 4 squared, and that equals v squared. 6 squared is 36, 4 squared is 16, 36 plus 16 is 52, and then that is equal to v squared. So to find v, we take the square root of both sides, square root of 52, and I believe that is 7.2 meters per second. All right, that's the magnitude, but that is not enough, right? We need two pieces of information. So we need to get magnitude and direction. We need both the v, the magnitude, the length of the hypotenuse, and we also need this theta to know what the direction is. I guess I'll leave that. So we use the cosine and the sine to find the x and the y components respectively. Now to get theta, since we were given the x and y, we can go back and we can use the tangent to find theta. So the tangent is equal to the opposite over the adjacent. And in this case, the vy is the opposite and the vx is the adjacent. So tangent is vy over vx. And over there, we're using that same, we're still working on this problem, so it's the same. Vy is 4 meters per second, and Vx is 6 meters per second. Units cancel, and we can do the inverse tangent. I guess that simplifies to 2/3. We can do the inverse tangent of both sides, and theta equals tangent to the -1 of 2/3. And you just plug that into a calculator. So we could write our final answer for this v given here with those grids used as meters per second. V vector is equal to 7.2 meters per second at an angle of 33.6 degrees. So that is an example of how to go from the given the x and the y components, how to go from there to the magnitude and direction. That's a very quick review of an intro to vectors. We also need to cover addition of vectors and multiplying by a scalar, and I'll cover those in a separate video.